What's up, guys? So, welcome back to another episode of System Design. And today we are going to talk about Google Docs and collaborative editing. So, today we are designing not just the storage or the sharing, the hard part, the real time collaborative editing. The part where people type in the same document at the same time and their edits do not destroy each other. Now, this is one of the most intellectually fascinating problems in distributed systems. It touches on consistency, concurrency, conflict resolution, and fundamental question of what it means for two people to agree on a shared state when they are connected over a network with variable latency. And it's a legitimate system design interview question. I have seen it at senior and staff level interviews when I gave on Google, Meta, or Notion. So today we will deep dive into it. We will cover the CRDTs, the more modern approach. Then we will walk through a concrete conflict scenario so you can actually understand how these algorithms work. And we will build out the full production system. So let's go. Now, what does a collaborative document editor need to do? Here are the functional requirements. First, multiple users can open the same document simultaneously and see each other's edits in the real time. The near real time means 200 milliseconds. The second is edits never corrupt the document. If two people type at the same time, both edits are preserved and in some consistent order. The three is users can see each other's cursors and selections, the presence awareness. The fourth is the document has a version history. Users can view and restore the previous versions as well. The fifth one will be the document persists. If all the users disconnect and reconnect later, the document is intact. And the sixth is the users can work offline. When they reconnect, their offline edits can sync without the data loss. Now, what are we not building today? The permission system, sharing model, commenting system, and mobile client. Those are important, but they do not change the core architecture of the real-time sync. Okay, so let's move to the non-functional requirements. First is the latency. The local edits must appear instantly in the local client. No waiting time for round-trip confirmation. This is called optimistic updates. The user should never feel latency when they type. Then we have eventual consistency. All clients must converge to the same document state. Even if two clients are temporarily out of sync, they must end up with the identical documents. Then we have availability. Users should be able to read and edit documents even if the part of the backend are degraded. Offline editing is a form of this. Then we have consistency on merge. When two concurrent edits conflict, resolution must be sensible, not arbitrary and not data destroying. Then we should be talking about scale. We have tens of millions of active documents, thousands of simultaneous collaborators per popular document, then millions of total active users. Now, the core tension here is between the low latency and strong consistency. To show a user their own keystroke immediately, you must apply the edits locally before confirming with the server. But what happens when the server rejects or transforms your edit? You have to handle that without confusing the user. Now, this is the fundamental challenge the entire architecture is designed to solve. Okay, so let's put the numbers to the problem in the form of capacity estimation. For active documents, we have around 100 million documents with at least one edit in the past 30 days. Then concurrent editing session. We can assume that 2% of the documents have active users at any given time. That is 2 million active editing sessions. Then what about the edits per second? A typical user types around 40 words per minute and 5 characters per word. That is 200 keystrokes per minute or about 3 keystrokes per second. Then across 2 million sessions, it means that there will be 6 million operations per second. Okay, now what about the WebSocket connections? We have 2 million concurrent WebSocket connection. Each WebSocket is a persistent connection. Now with 10 KB of RAM overhead per connection on the server side, that is around 20 GB of RAM just for the connection state. And this is very significant. The message size, now each operation is very small. It can be either insert or delete operation, and it may be around 50 bytes, including the metadata. So 6 million operations per second at 50 bytes, which is around 300 MB per second of operation data flowing through the system. Now, storage. A document is typically a few hundred KB. 100 million documents times 200 KB average is around 20 TB of document bodies. The version history multiplies this by some factor, say 10x, so 200 TB for all the versions. The key insight for this estimation is the WebSocket connection management is the scaling bottleneck, not storage or compute. Your architecture must handle millions of persistent connections effectively. Okay, now let's define the interfaces. The client connects with the WebSocket. The WebSocket is the primary channel. REST is used only for the document CRUD, create, open, get history, and close. So here are some of the REST APIs. We have the POST API that is for the documents. The response type is the doc ID and the initial version. Then we have the get document, document ID. In that, we have the response that is doc ID, current version, and the snapshot content. Then we have the get ID for the document ID history. We can get the history of those docs. After that, we have the WebSocket messages. These are the two types. First is when the client sends an operation. It is a JSON format. It has a type op, doc ID, ABC123, then the client version, and the operation. Is it insert at position 15 and the text is hello. Similarly, it could be an update or delete also, which is defined inside the op. When the server broadcasts the transform operation to all the clients, this is the form of the JSON that is formed. It has type op, doc ID, and the server version, and the operation which has happened. Did you notice that the position changed from 15 to 18? Now that transformation is the heart of OT. We will explain why and shortly. Now we have the data model, the document record, the operation record, and the snapshot record. In the document record, we have doc ID, owner's user ID, created timestamp, current server, version number, and the reference to the current snapshot. Then in the operation ID, we have the operation ID, document ID, server version number, client ID, operation type, and other fields. Similarly, then we have the snapshot record in which we have the doc ID, version number, full document content as string and timestamp. The snapshots are created periodically and for every 100 operations. So you do not need to replay all the operations from the beginning of time to reconstruct the document. Now for storage operations, we go to the relational databases like Postgre or append-only lock like Cassandra. Then snapshots go to the object storage. The current document content is cached in Redis or fast reads where the users can open the document easily. Let's walk through the high-level design through the big picture of it. So the system has four main components. The first is the client, the session service, the OT engine, and the storage layer. The client runs in the browser or the native app. It has a local copy of the document. It applies the local operation immediately without waiting for the server confirmation. The session service manages the WebSocket connection. It routes operation to the right documents. It broadcasts the transform operation to all the collaborators on a document. And the OT engine, the transformation logic. It takes two concrete operations, figure out how to apply both without destroying the data. And then we have the storage layer. This persists the operations and their snapshots. Now here is the request flow for a single keystroke. When user presses a key, the client creates an operation. Insert character X at position P at my current version N. The client immediately applies this operation to its local document. Then simultaneously, the client sends the operation to the server over the WebSocket. The server then receives the operations. It may need to transform it against operation it received from other clients while this operation was in flight. Then it applies the transform operation to the server document. It increments the server version. It broadcasts the transform operation to all the other clients connected to this document. Those other clients apply the operation to their local documents. Now here are the key insights. The client never waits for server confirmation before showing the user their own keystrokes. The latency is invisible to the local user, but this means the client's local version and the server version can diverge temporarily. Now, OT and CRDTs are what reconcile that divergence. All right. So now we will go to the core part. We will do the deep dive in all the components now. Let me make the OT concrete with an example. Now, this part requires the most explanations. They just say transform the operations and expect you to understand. But we are going to actually walk through it. So imagine a document with the text AC. Two users are editing it simultaneously. User 1 inserts B at position 1. The document then becomes ABC. Now user 2 inserts D at position 1. The document now becomes ADC. Now here is the problem. Their operations happen at the same time. Neither user knows about the other's edit. User 1 sends their operation to the server, then user 2 sends their operation to the server. The server then receives them both. If the server applies users 1 insert first, the document becomes ABC. Now it needs to apply users 2 operation as well and insert D at position 1. Now if it applies this naively, the document becomes ADBC. That is correct. But the D went in at position 1, pushing B and C to the right. But what about user 2's client? User 2 already applied their own operation locally. User 2's client C ADC. Now the server sends user 1 operation insert B at position 1. Then user 2's client applied this naively and gets ABDC. The two clients now have a different documents. ADBC on user 1 client, ABDC on user 2 clients. Now this is a divergence and this is the problem OT solves. Now here is how OT fixes it. When the server receives users 2 operation insert D at position 1, it knows it has applied users 1 operation insert B at position 1, which happened at the same time and the same version. The server transforms user 2 operation against user 1's operation. The transformer function asks, given that B has inserted at position 1 before I apply this operation, should my position change or not? The user 1 inserted at position 1. User 2 wants to insert it at position 1 as well. Since user 1's insert was before or at the same position, users 2 position shifts right by 1. So users 2 transform operation is now insert D at position 2. Now both clients converge. Server documents becomes ABC, ABDC. User 1's client receives users 2's transformation operation, inserts D at position 2 and applies it. Now ABC becomes ABDC. User 2's client receives user 1's operation, insert B at position 1 and transforms it before applying. Now B is inserted before D, so D shifts to 2 positions. Now ADC become ABDC here as well. Now both clients now show ABDC and that's how it is converged. So this is called operational transformation. The core idea before applying a remote operation and transform it to accounts of all other operations that happen concurrently. The transform function has 2 rules for insert conflicts. Rule 1, if the remote operations position is less than or equal to the local operations position, shift the local position right by the length of the remote insert. Then rule 2 is that if the remote operations position is greater than the local operations position, then no shift is needed. Now one more thing, insert delete conflicts have their own rules. Delete has rules. The full set of transform function for all operation pair is what OT system implements. It is tedious, but it is deterministic. The next component is session and version tracking. Now let's talk about how the servers track versions to know which operations need transformation. Each operation from a client includes the client current version. This tells the server, when I made this operation, I had seen all the server operation up to version N. If the server is currently at version M, where M is greater than N, the server knows that the operation at version N plus 1 through M are applied concurrently with the client's operation. It needs to transform the client's operation against those M minus N. The server maintains an operation log keyed by document ID and version ID. When a new operation arrives, the server looks up for the operation after the client's version and transforms the incoming operation against them in order, applies the transformed operation, increments the server version, and then broadcasts. This works fine for small documents and small divergences. But what if a client is offline for an hour and accumulated 500 local operations? Now the server needs to transform those 500 operations against the potentially thousands of servers operations that happened while the client was offline. and this can be very expensive. Now, for offline sync, we batch the operation and use more efficient reconciliation approach, which brings us to the CRDTs. All right. So the CRDTs is conflict-free replicated data types. The CRDTs are the alternative to OT. Instead of transforming operation at merge time, CRDTs are designed so that the operation can always be applied in any order and the result will be the same. The mathematical property is called commutativity and idempotence. A plus B equals B plus A. Applying the same operation twice has the same effect as applying once. So for collaborative text editing, the most common CRDT is called log oot or RGA, replicated growable array. The idea is to assign unique, stable identifiers to every character in the document. In a regular array, the characters have positions. Position 3 is the fourth character. If someone inserts a character before position 3, all the positions after it shifts. Now, this is the root cause of OT's complexity. Now, in a CRDT, every character has a unique ID that never changes. Even if the characters before it are inserted or deleted, instead of inserting at position 3, you say insert after character with ID X42. The position X42 doesn't matter. It's a stable anchor. Deletion works with tombstone. You do not actually remove a character, you mark it as deleted. The tombstone says in the document structure, when two clients both delete the same character, both operations says mark X42 as deleted. The result is the same. X42 is deleted, then no conflict. The trade-off is tombstones accumulate. And a document that has been heavily edited for years might have millions of tombstones taking up the memory. You need to periodically do garbage collection, but only when you can guarantee all clients are online and have applied all their operations. Otherwise, you might need to replay an operation that references a tombstone character and then it's gone. Now, we can discuss that how is OT and CRDT different? Which one is the right choice? Now, OT is simpler to understand. It has been battle tested. The Google Docs use OT-based Wave protocol for years, but OT requires a central server to serialize the operations. There is a single source of truth for the operation order. Peer-to-peer OT is theoretically possible but extremely complex. Now, CRDTs are inherently peer-to-peer. They work without the central coordinator. This makes them better for offline first applications. Notion uses CRDT, Figma uses CRDT, Apple Notes offline sync uses CRDT variant. So the modern answer is use hybrid. Use OT for real-time active sessions where latency matters most. Use CRDT like approach for offline sync where the commutativity is the priority. But for an interview, you should be able to argue either sides and explains the trade-off. Starting with OT and knowing where it breaks down is a solid answer. Now, next is the WebSocket session management. So let's talk about the session layer. This is where the scaling challenge lies. When a user opens a document, we need a WebSocket connection between the clients and the server process that knows about the document's current state. We need to route all the clients editing the same document to the same process, or we need the servers to process and coordinate with each other. Option 1 is the sticky sessions, and option 2 is the shared state in Redis. For sticky session, all client editing the document D go to the same server. A load balancer with the consistent hashing on document D ensures this. Simple to implement, but the problem is if the server crashes, all clients editing that document lose their connection simultaneously. That leads to reconnection thundering herd. Then option 2 is the shared state in Redis. Each server process is stateless. When an operation arrives, the server fetches the current document state from Redis, applies the transformation, stores the result back to Redis, broadcast via PubSub channel, and all servers subscribe to the document ID channel receive the broadcast and forward to their local clients. So option 2 is more resilient but has a higher latency due to the Redis round trip. For interactive editing, where every keystroke is an operation, adding a Redis round trip on the critical part matters a lot. In practice, Google Docs uses a document server that owns a specific document for the duration of editing session. The ownership is tracked in the coordination layer like Zookeeper or etcd. When all the users leave a document, the document server checkpoints state to durable storage and then releases the ownership. Now here is the life cycle. When the user opens document, the client makes a REST request to get the current snapshot. Then the client establishes a WebSocket connection with the session service. The session service assigns a document server for this document, either an existing one or if other users are already editing it or a new one. The client receives a session token and the current session server version. Then user edits. The operations flows from the WebSocket. Other users' operations come back. If the user closes the document or goes idle, after 30 seconds of inactivity, the session may be downgraded. And after 5 minutes, the WebSocket is closed. The final snapshot is written to the durable storage. Now, what if the reconnection happens when a client reconnects? It sends its last known server version. The server returns all the operations since that version. The client replays them to catch up. This catch up replay is why we keep the operation log. The operations are the source of truth. Snapshots are just performance optimization to avoid replaying the entire history. So the next component is presence and cursor sync. When multiple users are editing a document, you want to see each other's cursor, and this is called presence. The cursor updates are high frequency. Every mouse move or a keystroke might generate a cursor position update. But unlike the document operation, missed cursor updates are acceptable. If I miss the one position cursor update, the next one will correct it. Cursors are the best effort. For this reason, the cursor updates do not go through the OT engine. They go through a separate, lighter weight PubSub channel. The cursor position is expressed in terms of the stable character IDs from the CRDT model or in terms of a document offset with the current version. The client knows how to translate a position to its local document state. Now, the present state tells who is in the document, and this is stored in the Redis with the TTL. Each client refreshes its presence heartbeat every 10 seconds. If a heartbeat is missed, the user is considered gone. Now, this ephemeral state does not need durable storage. The presence payload includes user history, display name, avatar URL, cursor position, and selection range, if any. Now, this is broadcasted to all other clients in that document. Now, at scale, if a document has thousands of simultaneous editors, think of a company-wide shared doc, broadcasting every cursor update from every user to every other user in ON squared. This is very unsustainable. At high participant counts, you throttle cursor updates, batch, and send at most once per 100 milliseconds and only broadcast to the clients in the active viewport region. The next component is the version history with the CRDT tombstones. Version history is the ability to see what a document looked like at any point in the time and restore it. With OT, every operation is stored at the operation log with a server version number. Now, to reconstruct the document at a version 200, you start with the nearest snapshot at and before version 200 and replay operations from there. That's straightforward. Now, with CRDTs using Tombstone, the version history is tricky. Tombstones are character marked as deleted. Now, to show that document at an earlier version, you need to undelete characters that were tombstone after that version. This means filtering tombstones by the timestamp they were created and not just whether they exist or not. Now, each tombstone carries the server version at which it was created. To reconstruct that version 200, include all the characters alive at version 200. That means the characters created at or before version 200 and not tombstone at or before version 200. Now, this is elegant but memory intensive. All tombstones must be kept to support the arbitrary history reconstruction. Garbage collection tombstones mean capping how far back your history goes. Now, in practice, we store the tombstones with their creation version, a set of history retention policy, say 30 days or 1000 version. After that, run garbage collection. Tombstones older than the retention window can be safely deleted because no user will be restoring to a version that old. Now, here are some of the questions which a principal engineer might challenge you on. So what happens when the OT server loses the state? We can ask the diamond problem in OT. Considering the scenario client A and B both diverge from version 10, then client applies operation A, then client B applies operation B. Now the client A applies a transform version of operation B, client B applies a transform version on operation A. The document should converge. But what if they do not? This is a scenario-based question which you can be asked in a principal engineer round. All right. Now let's move to the next section, that is observability and monitoring. Now, what do you instrument in the system? We talk about end-to-end latency from the moment a user presses a key to the moment the operation is visible on another client screen. This is your most important user facing, that is P50, P95, P99. Alert at P95 exceeding 500 milliseconds. Now, operations throughput. Operations per second per document and globally. Alert if this drops unexpectedly. Then we have transform latency. It tells how long does the OT engine takes to transform an incoming operation. This should be under 1 millisecond. If it spikes, you have a document with very high concurrent operation volume. The WebSocket connection count and churn rate should also be considered. This tells about how many connections are being established and dropped per second. A high churn rate suggests network instability or client bugs causing the frequent reconnects. Then we have the convergence monitoring. Now, this is a hard one. Are all clients actually converging to the same document state? You cannot check this directly in real time, but you can do this periodically. Take a hash of the document contained as seen by the server, compare it against the hash reported by a sample of clients. The divergence means a bug in the OT implementation. Divergence should be zero. Any divergence detected is a P0 incident. Then we can have session metrics, the average editing session length, number of concurrent editors per document, the reconnection rate. If we have high reconnection rates, it suggests session server instability. For tracing, every operation should carry a trace ID through the WebSocket, the OT engine, the operation log, and the broadcast. When a user reports my edits disappeared, you look up the trace to see exactly what happened to their operation at each step. All right, so we have discussed a lot of details about Google Docs. Now let's zoom out. Real-time collaborative editing is hard because it is a distributed system problem in disguise. You have multiple nodes, the clients that need to agree on a shared state, the documents in the presence of network latency, and the concurrent updates. The two fundamental approaches are OT and CRDTs. The OT transforms operation at application time. CRDTs make operation inherently commutative, so order does not matter. So these are the key decisions we made today. OT for real-time active sessions because it is simpler, server-mediated, ordering side steps, TP2 issues. CRDT for offline sync because commutative operations make large divergences and it merges them efficiently. WebSocket is used for transport with Redis PubSub for cross-server broadcast. We use table character IDs for anchoring cursors, comments, and the version histories. Then we use write-ahead log before acknowledging operations for crash safety. Now, if you're walking into an interview and they ask you to design the Google Docs, start with the conflict scenario. Draw two users editing the same document. Show what happens without the OT. Then show what OT fixes it. The demonstration of understanding the core problem is what separates a good answer from a great one. Now that's it for today. This was a deep dive one. If you made it this far, thank you for watching. Hit like, subscribe, and drop your questions below. See you in the next one.